Okay, you are welcome for this webinar. Our speaker today is Sami Baraket. Sami Baraket is a full professor at Imam University in Riyadh. Sami Baraket obtained a degree in mathematical sciences in 1990 at the Faculté des Sciences de Tunis, and a PhD of mathematics in 1994 in the Center of Mathematics and Their Applications at l'École nationale supérieure de Cachan in Paris, in France. And he obtained also an habilitation universitaire in mathematics from the Faculty of Science of Tunis, Faculté des Sciences de Tunis, and from 94 to 96, he was assistant professor at Faculté des Sciences de Tunis. From 96 to 98, he was assistant professor at the same university and full professor from 2003 to 2008. And from 2008 to 2013, he was full professor at King Saud University. And again, from 2020, full professor at Faculty of Science. And now, since the starting of this university year, he is in Imam University. Sami Baraket was also the founder and director of the lab, research lab of nonlinear analysis and geometry, and a fellow of nonlinear analysis and partial differential equations committee at King Saud University. Sami, thank you for accepting our invitation, and you have 50 minutes to present your work, please. Thank you very much.
Okay, thank you, Nabil, for this presentation. I will begin my talk. The problem what we will deal today arise from essentially from geometry and physics. More precisely, if we consider some Riemannian surface endowed with its metric J0, we want to find a new metric GW conformal to J0. Conformal means that JW, we can write it as a positive function multiplied by the old metric J0. The new and old Gauss curvature are linked by equation 1. Now, in the equation 1, there is minus Laplacian J0 is the Beltrami Laplacian. Kj0 and Kjw are respectively the Gauss curvature with respect to J0 and Jw. Now, if we consider the metric flat and the remaining surface, the whole space R2, so Kj0 is equal to 0, and the Laplacian, the Beltrami Laplacian is the classical Laplacian, and equation 1 becomes minus Laplacian W equal to Jw exponential 2W. Now, if we want that the new Gauss curvature is constant on every point of R2, we will denote Kjw by
Sami, please, just one moment. The sound is not good. I don't know if you can improve it. I don't know how, but do you think that you can improve it?
Well,
Did your micro enough close to you, or?
But perhaps now it's better?
Yes, it's better, yes.
Okay.
So, but I think that there is two people that their mic, Abdul Wahid and Muhammad something, Abdul Qadir. So please kindly unmute yourself.
Okay. So the equation 1 becomes minus Laplacian u equal to rho square exponential u in R2. This equation has been well studied by Liouville. He gave all solution of this equation using complex analysis. Now, if we study this equation on some domain omega of R2 with Dirichlet condition, Suzuki and later Nakazaki consider the problem in one time with nonlinearity exponential u, and in the second time with nonlinearity dominated by exponential u. And we want to study the behavior of the solution of these problems. So they prove the following results. Two depends of the quantity sigma rho, which equal to rho square integral or of exponential u rho dx. So if sigma rho tends to 0, then u rho converge uniformly to 0. See, if sigma rho tends to infinity, then u rho tends to infinity on every x on omega. And the interesting case is the third. If sigma rho tends to some constant which which is 8 pi n is some integer, then u rho converges to some limiting function u star, which is harmonic except on a fine point z1, zn, exactly n point, where the location of these points are given by some functional a, given by the following expression, which depend on the green function of Marian Laplacian on omega and its regular part. So u star is simply sum of g between 1 and n of j dot zg. Now, in the first time in collaboration with Frank Paccard, and in the second time with collaboration with Danguier, we were interesting to the inverse problem, which is the following: given z1, zm critical point of the function E, can construct a family of solution u rho, which converges as rho tends to 0 to the limit function u star given by the point z1, zn fixed in the beginning. So we give a positive answer to the case of nonlinearity exponential u, and the case of nonlinearity dominated by exponential u as a classical model is f of u exponential u plus exponential gamma u with gamma between 0 and 1. Later, Esposito has considered the same problem on omega of R2 by adding some Dirac masses given by some 4 pi alpha I delta pi. And using this transformation, we can write the problem 7 as the problem 8 minus Laplacian v equal to rho square capital V exponential v on omega v equal to 0 on the boundary, where capital V is some potential which depends on the Dirac point pi between 1 and the capital N. And he give some discussion between the interception of the blow-up point and the Dirac mass. I mean, but blow-up point of solution U is some point in omega such that for rho fixed U is regular on this point, but when rho tends to 0, U rho on this point tends to infinity. What I means by blow up point of solution U. So we is possible to prove that if the blow up point are the Dirac point, so under any condition he can construct solution U rho which converge to the suitable to the desired profile. Now, if the blow-up don't intercept the Dirac mass, so he can also construct a solution U rho which blow up on the Qi I between 1 and n. Now, if we have blow up as a Dirac mass and no, so the solution U rho will converge to the desired profile, but under some condition of location of the blow-up point given by the functional f and the functional j. F is given also by the green function and its regular part. Now we will we are going now to the system. The first who study the system is Shanyu and Kisling. He consider the following system minus Laplacian U I equal to exponential sum of gamma Ig Ug under the condition that the energy is finite and the matrix gamma Eg in GLN of R, and line by line, if we add the coefficient, we find 1. So for every I fixed sum on J of gamma Eg equal to 1. He proved that necessarily all Ui are some function U, which is radially symmetric and decreasing about some point. This function is the function of this solution is the solution of Liouville, which is known on R2 on all R2. Now, also this problem has application in physics and geometry. In physics, in the charge of particle beams, and in geometry also in the construction of new matrix, which has some Gauss curvature prescribed. Now, in order to simplify this kind of problem, we consider only 2 equations, and in the first time, Nihed and Mariam Trabelsi consider the following problem with 10, and they constructed a solution U1 and U2 when the set of blow-up are disjoint. U1 is have a blow-up on point Z1, ZP, and U2 have a blow point ZP plus 1 Zn. Later, in collaboration with Bazar-Besha, we add some Dirac masses, delta P1 and delta P2, and we obtain a similar result as Mariam and Nihed Trabelsi. After this, we consider a system 12, which is minus Laplacian V1 equal to rho square exponential gamma V1 plus 1 minus gamma V2, and minus Laplacian V2 equal to rho square exponential Xi V2 plus 1 minus Xi V1. We have the configuration here. We have the configuration of Shanilu and Kisling. We note that when we add the coefficient, we obtain 1 in the first and second equation. And here we construct a solution V1 and V2 where the set of blow up is not necessarily disjoint. In the other way, V1 has Z1, Z2 as a blow up point, and V2, for example, has Z2 and Z3 blow up point. So Z2 is a common blow up point of to V1 and V2. Now we will consider the principal problem that we will that I will try to present today. So we will consider the same system as Sanoni and Trabelsi, but we will add 2 Dirac mass in the first equation and 2 Dirac mass in the second equation. We remark that the Dirac mass is delta P1, delta P2, and the Dirac mass are delta P2, delta P3 in the second equation. So we will discuss the set of blow-up point and the set of Dirac mass. There is essentially 2 cases. When the blow-up point is equal to when the common blow-up point of V1, V2 is equal to common Dirac mass to the equation 1 and the equation 2. For example, if we want to construct a solution which have V1 which have Z1, Z2 as blow-up point, and V2 which has Z2, Z3 as blow-up point, we will discuss the case Z2 equal to P2 and Z2 is different to P2. Okay, but and in these 2 cases there is a sub cases which we'll describe later. So if we consider the same transformation, we will have the problem 14 with a potential V1 and V2, capital V1 and capital V2. V1 is given by dot minus P1 power 2 alpha 1, dot minus P2 power 2 alpha 2, V2 dot minus P1 2 alpha 2, dot minus P3 2 alpha 3. F1 and F2 are a non-negative function, but in PI we want to be positive. F1 P1 P2, F1 P2, F2 P1, F2 P2 positive. Okay, so consider now the first case when Z2 equal to P2. There is 3 subcases. Z1 equal to P1, Z3 equal to P3, Z1 equal to P1, Z3 different to P3, and Z1 different to P1 and Z3 different to P3. In the first time, we will localize the position of the blow-up point. So our first result is the following. We will consider the second subcase, because the first subcase, P1, P2, P3 are known. So if we will construct Z1 equal to P1, Z2 equal to P2, Z3 equal to P3, there is no localization of the blow-up point. Now, for the second subcases, if we want that U1 blow up on P1, P2, and U2 blow up on the P2, Z3, then necessarily Z3 is the critical point of the functional E3 given by F1 Z3 plus logarithm of this quantity. F1 is a functional which depends on the green function and its regular part H. Now passing to the second case, when Z1 to the third case, when Z1 is different to P1 and Z3 is different to P3. And if we want that U1 row blow up on Z1 P2 and on Z3 P2, then now Z1, Z3 is the critical point of the functional E2 given by this expression, where F2 also is a linear combination of between the regular part, the green function and its regular part. Now we will do our construction. So if we are in the first sub case, we will choose F1 and F2 on P2 such that this equation, this relation holds. Now, we will assume that gamma and psi, alpha 1 and alpha 3 satisfies this condition. Then we construct a family of solution U1 row and U2 row which have the desired profile. What I mean by desired profile, I mean that U1 row blow up on P1, P2, and U2 row blow up on the P3, P2. You see that we have any condition on the position of Z1, Z2, Z3, because Z1 is equal to P1, Z2 is equal to P2, and Z3 is equal to P3. Now, we will consider the second and the third subcases. We will suppose that gamma psi and alpha 1 and alpha 3 satisfy the condition 18. This condition is satisfied when alpha 1 and alpha 3 are large enough and gamma and psi are close enough to 1. So we will suppose that F1 and F2 on P2 satisfy this condition in this subcase, and Z3 is the critical point of the functional F1 Z3. Moreover, we will suppose that F2, the gradient of F2 on the point Z3, of course, F2 with this function on the point Z3 is equal to 0. If we combine this condition and the fact that Z3 is a critical point of F1, we obtain the condition given in the last theorem when we try to find the position of the point Z1, Z2, Z3 on omega. So we can construct U1 row which blow up on P1, P2, and U2 row which blow up on Z3, P2. Finally, in the first case, the case when Z1 is different to P1 and Z3 is different to P3, we have a condition on the value of F1 and F2 on P2 must be satisfied, and now we want to add the gradient of F1 on Z3 and the gradient of F2 on Z3 is equal to 0. Then, under this condition, we prove that we construct a family of solution U1, U row, and U2 row, which have the desired profile. So now we'll turn to the second case when Z2 is different to P2. Also, we have three subcases: Z1 equal to P1, Z1, Z3 different to P3, Z1 equal to P1, Z3 equal to P3, and Z1 different to P1, and Z3 different to P3. So in the first time, we want to localize the position of Z1, Z2, Z3. After knowing this position, we try to construct the family of solution which have the desired profile as rho tends to 0. So we will give a similar result to the first case. So if we want to construct a family of solution which blow up on P1, Z2, and U2 blow up on Z2, Z3, then Z2, Z3 must be critical point of the function E1 given by this expression, and F1 Z of Z1 of Z2, Z3 is given also by this expression, which is a linear combination of the green function and its regular part. The same thing for the second subcases, and the same thing for the third subcase. So in each subcases, we must have Z1 or Z2, Z1, Z2, Z3, or Z1, Z2, Z3 critical point of some functional E1, E2, E3, which essentially have two types of terms. The first term is a linear combination of the green function and its regular part, and the second term is a logarithm of some quantity which is given by Z2 P1, Z2 P2, Z3 P1, Z3 P2. Also, you have the expression of these functionals. Now we will begin our construction. So we consider first a cutoff function which is one near Z1 and Z3 and vanish far Z1 and Z3. Also, we must have some condition between gamma psi alpha 1 and alpha 3. And we construct a family of solution in the first subcases when Z1 equal to P1 and Z3 different to P3, under the condition that Z2, Z3 is a precritical point of F1, and the gradient of auxiliary function on the Z2 and Z3 are equal to 0. So these conditions are satisfied by choosing the suite tuple F1 and F2 in each subcases. For example, here F1, the comportment of F1 and F2 on the point Z2 and Z3 is chosen such that this condition is satisfied. Now, if we have this condition, we construct a family of solution U1 rho and U2 rho, which blow up on the P1 and Z3, but in the common point, blow up point. Unfortunately, we cannot construct U1 rho and U2 rho separately. We construct a linear combination between U1 rho and U2 rho near the point Z2. The same thing in the same case under other condition. And the same thing in the third subcases under also some suitable condition. In Z1 and Z3, there is no problem, but in the common blow-up point, we construct a linear combination between U1 and U2. Now, in order to construct U1 and U2 separately, we must add other condition on the domain. So suppose that F1 and F2 on Z2 are linked by this relation, and we will suppose that on Z2 we have this relation satisfied with its gradient. This relation is cannot be satisfied on all domain, but on some domain with some symmetry, this condition are satisfied. So under the similar condition on F1 and F2 on the point Z2 and Z3, we construct a family of solution U1 and U2 separately with the desired profile. The same thing in the second subcases, adding some condition on the geometry of the domain, also in the third subcases. Now, I will describe the idea of the proof of one case, or one subcases. So, first, we will work in some special space functional spaces, which called holder-weighted spaces. Essentially, the space C K alpha mu is the space of function U, which are CK alpha log of R2, and which decays at infinity as like R power mu. Now, if we work on the ball, CK alpha or CK beta mu of the ball is the function in CK beta log, and which have the comportment as R power mu near zero. Now, we will describe the type of solution that we will consider in our construction. This solution is given by Liouville. In reality, is not essentially the solution given by 31, but is the solution which will be given later. But we can easily obtain this solution by the solution of Liouville of the equation minus Laplace nu equal to rho square module z power 2 alpha exponential u in R2. Now, if we take alpha equal to 0, then we obtain the solution of minus Laplace nu equal to rho square exponential u in R2. We will do some contraction fixed point theorem later. So we will use the linearized operator around the solution of U alpha 2 and U2. So we denoted by L alpha 2 the linearized operator of the nonlinear problem Laplace nu plus rho square z2 alpha exponential u about the solution u epsilon to alpha. And we denote by L the linearized of the Liouville equation about the solution u bar, which is u when epsilon equal to 1 and 2 equal to 1, which give by this expression. We prove in the first time that all bounded solution of LW equal to 0 is linear combination of phi 0, phi 1, and phi 2 given by this function. Phi 0 and phi 1, phi 2 are obtained by the invariance of the equation of Liouville under some groups, phi 0 for dilation group and phi 1, phi 2 for translation group. Now, when we have the potential Z module Z2 alpha, we don't have the invariance with translation group, so the only bounded solution is phi 0 given by this expression, and in this case we don't have phi ni phi 1 or phi 2. So now using Fredholm theorem, we prove that if mu positive, then alpha L alpha 2 is surjective, and if mu is greater than 1, the operator L is surjective between C2 beta mu on C0 alpha mu minus 2. Also, the same thing for L alpha 2. And also, the Laplacian is surjective for nu positive between C2 beta nu on C0 beta nu minus 2. Now, we have to introduce some harmonical function on B1 with an arbitrary data on the boundary. So if we kill the first mode and the second mode, then the function h is in C2 beta 2, and we have the following estimate. So, this anterior harmonic function and exterior harmonic function, we will use it in order to gluing the solution obtained in some small ball and in outside these small balls. So we have also a harmonic function defined on R2 minus B1, which an arbitrary data phi tilde on dB1. And if we kill now only the first mode, we have C2 beta minus 1 of H is less than C phi tilde in C2 beta S1. Okay, donc we will consider now the case when Z1 equal to P1, Z2 equal to P2, and Z3 different to P3.
توسطه هو يبدأ.
Allô? Allô? Allô?
It's okay, Sami. I can't the micro for colleagues. Okay.
Okay. So I see that I said that there is some small balls. The range of these small bars are given by R epsilon alpha. If the blow up point is some Dirac point, and R epsilon if the blow up is not a Dirac point. So now our approximate solution is as the following. For example, here we want to here we want to construct a solution U1 with blow up P1 and P2. Okay, so in the bar P1 and of radius R epsilon alpha, we put the Liouville solution, and we add it some harmonic function. So this function has a problem in Z3, but we are far of Z3 because we work here in the bar centered on P1 and the radius is very small. The radius tends to 0 when epsilon tends to 0. So this is harmonic. This is also harmonic, and this is constant. In P2, also we put the solution of Liouville, and we add to this solution some constant and harmonic function. Outside P1 and P2, we will put the desired profile. We do the same thing on U2 tilde in Z3, in P2, and outside Z3 and P2. We put the desired profile. So now we estimate our equation with this approximate solution. We find that it's of order R epsilon alpha, and R epsilon square. R epsilon alpha is something which tends to 0 when epsilon tends to 0. So our approximate solution is a good approximate solution. Now we will search our exact solution as our approximate solution. We will add it the harmonic anterior function and some function H11 which will be obtained by contraction fixed point theorem. The same thing for V2. We inject V1 and V2 in our equation. Then we will solve some problem like L alpha H11 equal. Here I put minus Laplacian H1 to 1. But why not L epsilon L alpha or L? Because in the ball centered on P1 and of radius R epsilon alpha, I want that U1 has a blow up on P1, but U2 has not a blow up on P1. So I will inverse only minus Laplacian, not L epsilon, not L alpha to 1. And then using the inverse operator, which I described it before, we have to solve the problem 40. And this problem is solved by using the contraction fixed point theorem. So we prove that there is H11, H21 such that U1 and V1 is exact solution of our system, and the norm of H11, H21 is of order R epsilon alpha. We do the same thing on the ball centered on P2 and of radius R epsilon alpha, and we do the same thing on we do the same thing on excuse me, we do the same thing on Z3 on the Z3 of radius R epsilon. And so we solve the anterior problem. After the anterior problem, here in Z3, we do the same thing. So I solve the anterior problem. And now we will go to the exterior problem. What I mean by exterior problem is the construction of our solution outside the ball centered on P1 and of radius R epsilon alpha, on P2 and of radius R epsilon alpha, and on Z3 and of radius R epsilon. So what we do in the exterior problem, we will put the desired profile, and we will add it some harmonic, some exterior harmonic function, and we will add to this some function which will denote it by H11 tilt. Okay, and we will do the same thing. We will use a construction fixed theorem to obtain exact solution outside the ball. So here we will do the same thing. So the function I denote it by V1 tilde and V2 tilde. And V1 and V2 of order R epsilon alpha square, which I mean that it's small and tends to 0 when epsilon tends to 0. The norm, I speak about the norm. Now we will gluing the solution obtained in the small ball and outside the small ball. So in the boundary of each ball, I will solve the equation U interior I minus U exterior I on the boundary of each ball equal to 0, and the normal derivative of U exterior I minus U interior I minus U exterior I equal to 0. But if you recall the interior harmonic extension and the exterior harmonic extension, the data on the boundary is arbitrary. So we will fix this data in order that the system 52 is satisfied. Then we will solve some nonlinear problem like the first, like T1 lambda 1 phi1 I tilde phi1 0 I tilde phi1. So you see that this nonlinear problem, there is the data of the exterior and interior harmonic function. So by Schroeder fixed point theorem, we will solve this system, and we obtain the desired solution U1 and U2 on all omega, and when epsilon tends to 0, we obtain the desired profile. Thank you very much for your attention.
Merci. Thank you, Sami. Is there some questions, please? Perhaps, do you have some questions? Okay, Sami, I want just to ask you a first question about the motivations of this. Is there some applications? Okay, because of course for the inverse problem it's clear, but the first part, this when you change the Riemannian manifold, okay, what was the motivation of that?
The motivation is that the Gauss curvature of with respect to the new metric it will be constant on any point on the remaining surface on omega, and this property is for some standard surface like the ball, like the cylinder, like. But if we take any Riemannian surface, the Gauss curvature is not the same at any point of the surface. So, but if you change the metric and you want to have a Gauss curvature which is the same on all the points, is very good as a property. Or also the Liouville equation has an application in the gas combustion. It has an application in geometry and in physics. Now, for the Dirac masses, the Dirac mass play the role of impurity in the the gas that we will to combust it.
Okay, okay. A second question. Did these results can be extended to 3D, or there is some, I think there is some difficulties. What do you think about these difficulties on to extend this work on 3D? Sami? I think we miss. Sami, do you hear me? We have a problem with the.
Hello?
Yes, Sami.
Oui, yes.
I ask you about the extension of your results in 3D. Is it possible? Is there some difficulties, or is it?
Yes, yes. Nabil, it is a very good question because in not 3-dimension, but I will speak about 4-dimension, because this problem arises from geometry, and when we work on some problems which arise from geometry, the conformal and variation is very important. So the exponential will be important when we associate it with the B Laplacian, but in R4, not in R3. Because if we want to do the same thing, not with the Riemannian surface, but with a Riemannian manifold, and now we want that not the Gauss curvature, but the Q curvature. This curvature is introduced by Penites, and we want that this Q curvature will be constant. So we will study the problem given by B Laplacian U equal to rho square exponential U, but with a Navier condition on the boundary, which is U equal to Laplacian U equal to 0 on the boundary. And we can do many things. With Frank Baccar, we will consider this problem, and we give a positive answer to the question given by Wei, and after this, with my students, we will study. We study the system case, and we have also results for Laplace. And we can do it in general for any other dimension with minus Laplacian power, the half of dimension. We can consider the non-linearity exponential u, and this equation is invariant under conformal transformation.
Thank you, Sami. Do you have other question, please? Yes, Fathi? No questions? Okay. If there is no other questions,
No.
Yes?
Yes, is my mic open?
Yes, it's open now. Yeah.
Okay. Thank you, Nabil. Thank you, Dr. Sami, for this very nice presentation. It covered many aspects of from Liouville to Fredholm to many applications. I think Nabil was asking the kind of applications. Perhaps this could be applied to even war times. For mine fields or petroleum oil fields and gas fields, etc. Like you said, like you mentioned earlier. In the chat, I sent some invitations to everyone about the group. Basically, the question that was asked by Nabil, that he said that could you extend this to 3-dimension? You said it could be extended to 4, but 3-dimension is kind of hard because maybe it's odd or something. I did not get the point. Why is it 4 but not 3, etc. But I'm sure perhaps it's explainable. But yeah, go ahead, please.
Perhaps I will give you some explication about the 3-dimension, because for the 3-dimension, if we want that the problem is well posed. I mean by well posed, that is there is the invariance of the equation of conformal transformation, dilation, translation. You must take as operator minus Laplacian power 3/2. You understand me? Which is not classical operator, but is a pseudo operator. When we work on R3 or R3, there is no problem because we can use the Fourier transform. But when we work, when we work on omega, a subset of R3, we have a few tools to do this problem, to do this construction. So the problem is much more difficult, and our operator is not linear now, because minus Laplacian power 3/2. You understand me? That is
it's no longer,
that is different. Exactly. I say that we can do it in
4.
Now there is a problem with
the voice. Yes. Okay. I understood what he meant.
Okay.
Anyway, yes. Maybe he will come back.
Okay.
Okay. Thank you.
Thank you.
Okay.
Thank you very much.
Okay, if there is no other questions, perhaps we can stop now. And thank you again, Sami, for your talk.
Thank you, Nabil, for you also.
I just want everyone to see the chat, please, to come to our group. Nabil is there, and Sami, you're welcome, and everyone else that is attending to the group. I sent you the link. It's called PAM, and it stands for Paradigm Shifts in Pure and Applied Mathematics.
Okay, thank you.
Most
Okay, I
welcome.
will-
Most welcome. Thank you.
Okay,
Thank you. It's a big
thank you
group.
very
It's
much.
160 people almost.
Oh,
Yes.
okay.
Okay, thank you,
Most
Fatih.
welcome. Salam.
Okay,
Salam.
thank you very much. Salam.